So, welcome back to the discussion on kinematics of nuclear reaction. In the previous class, I have started discussing the relation between energies of the projectile and ejectiles and the angle with which the ejectiles are moving with respect to the incident beam direction. All right. So, let us see more features of this kinematics of a nuclear reaction in the laboratory frame of reference. So, right now the discussion is on lab frame of reference. All right, fine. So, if you remember in the last class, I have ended the discussion with this expression of ejectile energy when the reaction is endothermic. It is endothermic, and we have seen that because there is no positive solution for ejectile energy, and for every value of theta, that is angle with which ejectile is moving forward with respect to the beam direction, there will be a minimum energy for projectile beam below which it is not possible for the reaction to happen, and the value of this minimum energy of the projectile is smallest when theta is equal to 0 degrees, which we termed as threshold energy. And at this threshold energy, what is the value of the energy of the ejectile? Nothing but the threshold energy multiplied by the ratio of these two quantities. All right. Now, so at threshold energy, the value of Ey at theta is equal to 0 given here. Now, if we increase the ejectile energy, projectile energy beyond the threshold energy of the projectile beam, beyond the projectile energy beam, then the ejectile, the product particle, I am not using the word product nucleus, I am confining to the measurement of product particles. It could be protons, it could be sometimes alpha, it could be neutrons, it could be gamma rays, right. So, they can be emitted at theta is equal to 0. Theta is greater than 0 degrees. Earlier it was only theta is equal to 0. Now, theta greater than 0 comes into picture when the projectile energy is greater than the threshold energy of the projectile. So, you need to understand the relation between threshold energy of the projectile beam and energy of the projectile beyond the threshold energy and the value of theta, the value with which the ejectile is moving forward with respect to the incident beam direction. Now, in this particular case, the expressions of R and S, if you see, it yield two positive solutions for Ey. Okay. Now, the theta value is greater than 0, but I am confining to less than 90 degrees. Now, you can see instead of one energy of the ejectiles, there will be two groups of different energies. What does it mean? At theta is equal to 0, the minimum energy with which projectile energy can initiate a nuclear reaction is threshold energy, right. And if you go beyond threshold energy values, then you will see up to 90 degrees, there will be two sets of energies for the particles. So, when you plan the experiment and keep the detectors with respect to the incident beam direction, this relation between the energies of the ejectiles and the theta values will be very useful to you. Of course, it is possible, it is valid when the projectile mass is much less than the mass of the product nucleus. All right. Let us see what more is there in store for us. Okay. So, there will be two particle groups of different discrete energies which are emitted in the forward direction, because I am confining theta to be less than 90 degrees. All right. Now, if the projectile energy exceeds the value of this q into my by my minus mx, then there will be single positive solution. So, you have to understand different scenarios in this case. Now, up to this I have considered a reaction in which particles are having rest masses. particles are having rest masses. I have discussed earlier that most of the reactions in nuclear astrophysics deal with radiative capture type, right. So, in this case ejectile is gamma, which has no rest mass. So, you need to replace few quantities if the nuclear reaction is radiative capture type. All right. What are the quantities to be replaced? Let us see. So, if the ejectile is gamma ray, then we call this reaction as a radiative capture. Now, use energy of the gamma in the place of total energy of the ejectile, that is rest mass of the ejectile and kinetic energy of the ejectile. This sum, whatever earlier, wherever we have used this rest mass plus kinetic energy of the ejectile, this you have to replace with this energy of the gamma, and square root of 2 me for the ejectile has to be replaced with energy divided by the velocity of light, right. That is how we represent the momentum. Now, do all this mathematics again by replacing these two quantities, that is total energy of the gamma and total momentum of the gamma, which has no rest mass. All right. Now, in the same way, in the similar way, we can eliminate the Ey and phi, then solving for E gamma, we get this expression. Solving for E gamma, we get this expression. So, this is basically capital I. Okay. And energy of the gamma in radiative capture reaction can be found using this relation. To study the nuclear reaction of interest, when we deal with the astrophysics, many times you come across radiative capture reactions. As I have said many times earlier, the measurement of gamma energy is very important, right. So, this energy of the gamma mathematically is sum of 4 terms, What are those 4 terms? Number 1, Q value of the nuclear reaction, all right. And then it is Q value of the nuclear reaction, and then the energy of the projectile in center of mass system, and Doppler effect, because recoil nucleus is moving with some velocity. What is that velocity? I will write down. This is this Vy is the velocity with which recoil nucleus is moving, and because the recoil nucleus is moving with this velocity, which can be written as velocity of the projectile multiplied with the mass of the projectile divided by mass of the product nucleus, right. So, because of the recoil nucleus is moving with a velocity Vy, there will be Doppler shift in the gamma ray. Not only that, because of the shift in the energy of the gamma, shift in the energy of the recoil nucleus, one has to consider the recoil shift as well. So, the energy of the gamma in radiative capture is the sum of these 4 terms, all right. And in general, these last 2 terms represent relatively small corrections, but of course, sometimes they may play important role. So, we need to have numerical expressions for last 2 terms, that is Doppler and recoil effects. What are those relations? Let me present here directly. The Doppler effect corresponds to the energy given in here in MeV, and then recoil shift energy corresponding to it is given by this relation in MeV, okay. And here all the energies are in MeV and the rest masses are in AMU, all right. So, these 2 relations corresponds to the last 2 terms in the energy of the gamma ray expression. But remember, in here if you see the 3rd term and 4th term, Doppler and recoil shift, on the right hand side you can see E gamma is there, on the left hand side also E gamma is there, isn't it? On one hand we are writing expression for the energy of the gamma ray, on another hand in 3rd and 4th term, which corresponds to the Doppler effect and recoil shift, E gamma term is coming into picture. This also has to be handled, okay. So, if we are okay with some kind of less accuracy, then we can write down the expression for E gamma as simply the sum of first two terms in the expression, that is Q value and the energy of the center of mass system, alright. But if you want better accuracy, then what to be done? Then replace the masses with the relativistic effects. Okay. This gives us energy of the gamma, this kind of relation. Okay. So, one can derive after seeing these relations, and all this discussion is available in the textbook, which is one of the important references for this course, Nuclear Physics of Stars, that is Iliadis. Alright. Continuing the discussion on the kinematics of nuclear reaction, the next question is, what is the relationship between angle with which gamma ray is emitting with respect to the incident beam and the angle with which product nucleus is moving with respect to the incident beam, which is characterized by the angle phi. What is the relation between this theta and phi? How to get them? Not very difficult. Okay. So, earlier expressions can be solved to obtain the expression for recoil angle, and you can see this expression that when theta becomes 90, this phi value is maximum. What does it mean? In the reaction, if this is the ejectile and this is the target nucleus, the gamma is emitted perpendicular to the beam direction, This is the case when theta is equal to 90, that is when gamma emits perpendicular to the beam direction, phi, that recoil angle, is maximum, and that maximum recoil angle is expressed by this relation, substituting theta is equal to 90 in the above expression. Alright. Now, when this is maximum, the recoil angle is maximum, that means the recoil nucleus B, it is emitted in the forward direction only, but into a cone of half angle phi max, Okay. So, let me provide a few comments on these relations. See, we have assumed that there is no beam energy loss in the target. This is very important. Otherwise, the projectile energy, if it undergoes loss within the target materials at different stages of its transport journey within the target material, then the projectile energy is changing. Then accordingly, for one particular case, when we fixed the projectile energy, then the whole scenario will change. So, the important assumption which we have made here is beam energy loss is ignored, okay? And then the reaction is induced with a bombarding energy in the laboratory frame of reference. So, next I will discuss the relation between laboratory and center of frame of references when we deal with the energies and the angles. Alright. So, with these assumptions, what are the comments I would like to make? If at all the projectile, after reacting with the target nucleus capital X, it may give particles or nuclei with rest masses or particle with no rest mass like gamma. So, it is a general case I am discussing. If the capital Y gets populated, okay, capital Y gets populated, that is the reaction populates an excited state in nucleus Y, then the Q value in the above expressions, they have to consider for the energy of the excited state also. Until now we have considered it is reaching to the ground state. We have considered the situation where the product nucleus capital Y is in the ground state, but it is quite common that the product nucleus goes into the excited state. It has some energy. So, when you deal with the Q value, it has to consider the effect of energy of the excited state as well. Okay. How to take into account? Very simple. The Q value is nothing but the Q value of the situation corresponding to the ground state of the product nucleus minus the excitation energy, very simple. Okay. So, this Q naught is nothing but the q value corresponding to the ground state of the product nucleus, ground state of the product nucleus. Now, it is very much possible that the population can be at different excited levels. Okay. So, for a fixed angle of emission of the ejectile, each of these states which were populated by the incident particle, each of these exit states will give rise to a different value of the energy of the reaction products. Remember, for a fixed value of theta, that means ejectile is emitting with respect to a fixed value of theta with respect to the incident beam direction. Okay. Different levels of this compound nucleus formed, in this case capital Y, they leads to the different value for the energies of the reaction products. It could be ejectile, okay, and the population of the ground state, if you consider, that is the largest observed energy. That is very simple to understand. Okay. Now, consider a case when the situation has to be discussed in center of mass frame of reference. What is the importance of CM frame of reference? From now onwards, I am going to use the word CM frame. From theoretical point of view, the motion of center of mass has no consequence in a nuclear reaction. So, in general, we prefer to represent the values like cross section, reaction rate or S factor, all these things in center of mass frame of reference. Okay. So, the cross section when we measure in the nuclear reaction, we deal with the quantities in CM frame of reference, because earlier when I have drawn the collision between two entities, I have shown you the way with which center of mass is moving, right. Now, in CM frame of reference, both projectile and the target, they are moving in opposite direction, so that center of mass is at rest. Center of mass is at rest. So, for the sake of convenience, let me draw both situations again. Okay. So, in lab frame, if you remember, in lab frame, small x, okay, it is moving, center of mass frame is moving, and we have taken the target nucleus, okay, and in this direction when we draw the things, it is before collision and after collision. How I have done earlier? It is the emission of ejectile with velocity y and angle is theta, and this is the way the center of mass was moving, and the angle with which product nucleus is emitted is phi, and this is basically capital Y moving with velocity y. All right. Here the momentum of the incident particle, because in lab frame target nucleus is at rest, okay, target is at rest, projectile is moving. So, when you apply the conservation of momentum, the momentum of the projectile is equal to the momentum of ejectile plus momentum of the product nucleus. All right. Now, in center of mass frame of reference, you can see that the projectile is moving in forward direction. Now, I am using a symbol prime. All primed quantities refers to the quantities in CM frame of reference. All unprimed quantities refers to the laboratory frame of reference. Okay. So, in CM frame, I am using prime symbol. All right. So, before collision in center of mass frame of reference, how to draw the things? So, here the center of mass is at rest and projectile is moving in the opposite direction. Projectile, that is projectile and target nucleus capital X, they are moving in opposite direction. So, V capital X prime and V small x prime. All right. And after collision, how to draw the things? So, this is after collision and this is before collision, right. After collision, you can see the product nucleus is moving, and here the ejectile, that is small y, it is also moving. Now, only one angle is coming into picture, that is theta prime, because in the CM frame of reference, products, that is ejectile and the product nucleus, they are emitting in opposite directions, because we are considering CM frame of reference, and there is no point in bringing the phi, that is recoil angle, into picture. All right, and this V y prime small y and V capital Y prime, in this particular case, momentum of projectile and small x, momentum of capital X is equal to momentum of ejectile, which is a vector, plus momentum of capital Y, which is also vector, it is 0. Total momentum before and after collision in CM frame is equal to 0. This has to be kept in mind when you try to solve the relations in kinematics of a nuclear reaction. All right. So, let us see how the relations looks like. So, this CM frame of reference is more convenient to use a moving coordinate frame in which the center of mass is at rest. Now, the non-relativistic effect, if we consider how the transformation of kinematic quantities looks like. And as I said, primed quantities refers to CM frame, unprimed refers to lab frame of reference. And as I said, in the CM frame, total linear momentum is 0, and this product entities, that is ejectile and the product nucleus, they will recede in opposite directions. So, there is only one scattering angle, that is theta prime, only one angle, that is theta prime. So, before the collision, what is the velocity of center of mass system? Okay. It is basically given by this expression, where the terms are self-explanatory. Now, I am talking about the velocity of the center of mass, okay, is given by this relation. All right. And what are the velocities of this projectile and target nucleus in the center of mass frame? Okay. Here it is given by the difference of projectile velocity and the center of mass velocity is nothing but the velocity with which projectile is moving in center of mass frame, and in terms of masses we can use this relation. All right. What about velocity of target nucleus in center of mass frame? Nothing but velocity of target nucleus minus velocity of the center of mass frame, and anyway it is 0, right, and velocity of center of mass frame is given here. So, in terms of masses we can write like this. So, the total linear momentum is 0 in the case of center of mass system, okay, fine. So, the total linear momentum is 0, giving rise to this kind of relation. So, this gives us an idea about the ratio of the velocities of projectiles and target nuclei, ratio of velocities of projectile and target nuclei. They are nothing but the ratio of masses of product nucleus and the projectile. Now, let us see how the kinetic energies of projectile and the target nucleus looks like in the center of mass frame, because we have written the velocities of small x and capital X in CM frame. Once we have the velocities in hand, by multiplying with half m and squaring the velocities, one can get the values of kinetic energies. So, how do they look like mathematically? So, Ex prime is nothing but half mv square, okay, and if you expand this, you will get this kind of expression, and simplifying leads to this kind of expression, which involves mass of the target nucleus and mass of the projectile, okay, and energy of the projectile. Similarly, energy of the target nucleus, kinetic energy is nothing but half mv square, where mv is the mass of the target nucleus, and velocity with which target nucleus is moving in center of mass frame. That is why we are using prime symbol. So, one can get this kind of expression. All right. Now, what is the total kinetic energy before and before the collision in the center of mass frame, and how it can be linked with the lab bombarding energy? Very simple. Take the Ex prime when projectile energy in the CM frame and target nucleus kinetic energy in the CM frame. Together you can get the total kinetic energy. All right. And here the Ex, if you see, it is the sum of Ei prime total kinetic energy and the EC the velocity total kinetic energy of the center of mass system, all right. And this Ex, if you expand, you will get this kind of relation, and similarly you can see that this energy of the projectile as the sum of total kinetic energy in the CM system, okay, and energy associated with the center of mass, fine. And Ei prime, as can be seen from this expression, it is the half mv square kind of thing, where m is the reduced mass of the projectile and target nucleus and velocity with which projectile is moving in the lab frame. So, that is why I have said how the relations can be related with each other. Now, the situation after the collision, how it looks like. What is the velocity? Writing this expression of the momentum, okay, we can write like this, and velocities of a small y and capital Y in the center of mass frame, we can write in terms of half mv square, and here I can use for the velocity of the product nucleus in CM frame, okay, from this relation expanding gives this kind of relation, okay, Ey prime. Now, total kinetic energy in the CM system after the collision can be given like, instead of Ei earlier, that is initial before the collision, after the collision we are writing small f, okay, and doing the routine mathematics, you will get this kind of relations. And how can we relate to this lab bombarding energy? Every time we want to relate how the quantity will look like when we relate to the incident particle energy, all right. So, Ef prime can be written in terms of q value and energy of the projectile, mass of the projectile and the target nucleus. So, all this mathematics one can do easily, and Ey prime ejectile kinetic energy in the CM frame and product nucleus kinetic energy in the CM frame can be obtained using simple algebra relations. And the final thing is how the angles and solid angles can be related in lab and CM frame. After the collision, if you see, the velocity of the ejectile is related by Vy minus Vc, which I have written earlier, okay. And if you take the components, it is 0, okay. Cos theta prime and sin theta prime, you can write the expressions like this, okay. And using those relations, one can come up with the tan theta, which relates to theta prime, and cos theta, which relates in terms of theta prime only, all right. Where here this gamma is not gamma ray, it is some constant, some symbol, okay. So, please do not get confused. So, this can be represented by this relation, okay, which can be approximated by this relation. And if we consider for the radiative capture, then this cos theta can be simplified as this relation, where you can see the relation between theta and theta prime, and where beta can be written like this, all right. So, to summarize today's lecture, I have related various quantities between lab frame and CM frame. Please work out all these relations yourself, and I have ended the lecture by relating the theta and theta prime when we come across lab frame and center of mass frame. So, in the next lecture, which is the final lecture of the nuclear astrophysics course, I will cover time of flight method and the essence of important indirect methods, all right. Thank you so much.